Lesson is a continuation of yesterday's. Yesterday's we looked at, all right, what happens if we're looking at expressions where we have to break up a radical into two different terms to simplify, to make it easier. Well, now today is what if we have to add or subtract them? And this is actually one rule. That's all it is. And it's actually a pretty simple rule. And I've always taught this the same way, and most students do really well. The issue that some students have in this section, not this section, but the idea of radicals, is they confuse like multiplying and dividing and simplifying with adding and subtracting. And they're different operations. So my rule is this. Think about this, and I might have wrote it on the... Think about this, as if they're variables. As if they're variables, all right? So simplify first, then combine like radicals, as if they were like terms, and treat them the same way. So for example, why can I not add these two expressions together? They don't have the same variables. They're not like terms. But clearly, I can add these two things together, right? That gives me simply 5x. Agreed? Now, what if you have the following instead? Take the same concept. What if I asked you to add radical 5 plus radical 3? Why can't I add those? Yeah, they're not like radicals. But what if I had this? What does that become? And be careful, it's not times, it's plus.
2 radical 5.
2 radical 5. Because you have a radical 5 plus another radical 5, so you have 2 radical 5s. So think about your radicals as if they're variables. It's the exact same way. But instead of a radical 5 plus radical 5, what if I did this? What if I had 2 radical 5 plus 4 radical 5? Well, now how many radical 5s is that? 6. So it's literally the same thing. So I'm going to underline for you. Think of these in front as the coefficients, right? Aren't they the coefficients up here? Those are the coefficients. And then think of the radical 5s, or whatever the radicals are, as the variables. Variable, variable, variable. So these two things are analogous. I use different coefficients, obviously, okay? But the ideas are the exact same thing. So when you see a radical, think of it as if it were a variable. Now, my recommendation as well is to simplify as far as you can before you try to add or subtract radicals. Simplify things first because it might not seem like they can be added or subtracted, but if you simplify, you might get the same radicand on the inside. And then you can add or subtract those terms. I want to start. How about part A? So this involves yesterday's lesson. So when you have this on your test, you could expect this kind of a problem to test you on breaking down radicals as well as adding them together. So how would I break these down? What should I break them into to make it easy on myself? What should I break radical 48 into? Remembering that I need to make it a perfect square. Mike, what do you got? How about 75, Mike? How about break up 75? That's the easier one. Good, 25 and 3. Now, I stopped and I asked Mike to break up 75 when he stopped there for a sec because it might help him with the other one. You follow what I'm saying? What's the non-perfect square to these two? Non-perfect. 3. So the radical 25 becomes just what? So it's 5 root 3. So there's probably going to be something root 3 here. You see what I'm saying, Mike? So Mike, put a 3 here and then ask yourself 3 times what gives you 48? 16. So make it easy on yourself. If you're adding radicals, there's a good chance you're going to have like radicals. So if you got a 3 for one of them, you're going to probably get a 3 for the other one. Okay, use your context clues the same way you would do in English. You know, if you're answering a question on a test, use the words around it. Use the numbers around it in the actual expression. No equation here. So this becomes 4 root 3 plus 5 root 3. Paul, how many root 3s is that? 4 root 3s, and then another 5 root 3s, 9 root 3s. Remember to add these two together. Think of those as coefficients. Okay, so again, I would think of this, and I'll put in parentheses over here, as 4x plus 5x. That's really what this line is telling me if I think of variables. I'm not actually going to do that, obviously, right? But that's what I'm thinking of. I'm thinking of 4x plus 5x, and that's really just 9x. So instead of 4x, we have 4 root 3, so it's 9 root 3. Try part B real quick on your own, and this is a cube, so you need to think about your perfect cubes. So think about what perfect cube goes into 16, what perfect cube goes into 54. and try to simplify that and combine like radicals. If you're getting good at this and finish quick, go to the next one, that's fine. So what's the perfect cubes in this example here? What perfect cube goes into 16 to start that one off? 8. 8 definitely goes into 16, and 8 is a perfect cube. So I think of this first one as 5 times the cube root of 8 times the cube root of 2. And then 54. If I see that I have a cube root of 2, I'm probably going to have another cube root of 2. So I'm going to guess that that's already going to be there. And if that's true, Luca, what goes in the other spot? 27, which is also a perfect cube. And at this point in time, I'm just simplifying. The cube root of 8 is 2. The cube root of 27 is 3. So the first term becomes 10 times the cube root of 2 minus 3 cube roots of 2. How many cube roots of 2 do we have left? Anybody? 7. Okay, 7 cube roots of 2. And in the third example, let's take a look. We have 50 over 3 under the radical, and then 2 over 3 under the radical. And this is up to you which way you'd like to start it. You can start this one by trying to rationalize. You can break it up, take a look at it that way. Yeah, sorry, but just this one, yeah. Anybody get this third one that wants to step us through what they chose to use? How did you go about solving this one? Because again, you can choose many ways. You can begin by rationalizing. You can begin by simplifying. You could even technically add because you have like denominators. Remember that? Common denominators you need to add. I'm going to give you another minute. How would you start this? What would you break 50 into? Kelly?
Square root 25 and square root 2.
Yeah, break this into 25 times 2. Which is really 5 radical 2. So that's a good beginning. All right. Again, there's more than one way to solve this now. We could try to rationalize each of these individually, or we could start by adding them because they have common denominators. When you add fractions with common denominators, what do you have to do? Like what's 1/2 plus, or 1/4 plus 3/4? How many quarters? 4 quarters. So what are you literally doing when you're adding fractions? You're adding what? The numerators. Are you touching the denominators at all? So leave the denominator alone. Okay, leave the denominator alone as your radical 3. And the numerator is 5 radical 2 plus 1 radical 2. There's really a 1 here. Think of this as 5x plus x. That would give you 6x. So it's 6 radical 2. And now at this point in time, I would, there's only one way to solve this or simplify this further, which is to rationalize the denominator. So how do I rationalize this denominator? What's the process? Sabine? Okay, so multiplying by what over what? Yeah, square root of 3 over square root of 3. So in essence, you're squaring the denominator, but you have to multiply by the same thing that's up top. So we end up getting 6 radical 6 over 3. All right, 6 radical 6 over 3. Is that it? Are we done? Well, can I simplify it? Makes this 2 over 1, right? So it just becomes 2 radical 6. Again, treat them like variables. Watch. Up here, if you had written this as 6x over 3, you would clearly simplify that. And that's what that is. This is 6x all over 3. So the 6 and the 3 would reduce to a 2 there. Okay, so apply the same rules you would apply with variables to this idea. So ones that are a little more complicated with variables follow the same rules that we just looked at, but you have to have like radicands again. So looking at the first one, it looks really messy, right? Doesn't that look really messy to start off? So that might be a bit of a headache to do. What would you do to solve this first one? Or to simplify, rather, not solve. To simplify this first one. How might you begin this? What's one way? Because there's more than one way to begin this. Again, I keep saying that. There's more than one way. So give me one option. Mike, what do you think? What should we start this with? Yeah. Let's break it up. What do you want to break it into? 6 and 8? That works, but are either of those perfect squares? So what's one that is a perfect square that does? Yeah, 16 and 3. So let's break this first one up into root 16 times root 3. That's good for the 5 radical 48. I agree. Now, looking at the next part, there's no way I'm going to be able to add like terms together the way it's written right now, because I see that I'm going to have to distribute. Looks like there's a multiplication going on there. So maybe I should distribute this -4 radical 6 to each of those terms. Well, let me go on the side and do this so you can see. I'm going to distribute this just like I would distribute in the past, the exact same way. But now I'm going to have, so this is going to be a -4 root 6 times 3 root 2. Oops, 3 root 2. And then I'm going to have to distribute it again. But when I distribute the first time, that's what I see on the top right. When I distribute the -4 root 6 to 3 root 2, that's what I see. How do I multiply two things? How do I multiply two things that involve radicals? And again, think about them as variables. If this had been -4x times 3y or something like that, what would you actually multiply? How would you multiply that? Again, think of them as variables. Imagine that this said -4x times 3y. What would that become?
-12xy.
Yeah, this would become -12xy. So in essence, Kelly, you're multiplying the coefficients first, aren't you? And then you're multiplying the two different variables. So here, let's multiply these coefficients first, which gives me a negative 12. And then I can multiply radical 6 times radical 2, and they're both under the radical. So that's going to give me radical 6 times radical 2. What is it?
12.
Radical 12. Remember from yesterday's lesson, we broke things up. Like Mike broke up 48 into 16 and 3. Didn't you, Mike? So technically, 6 times 2 can go back to 12. So not only can you break things up, but you can multiply under the radical together. The same thing goes for the next part here. If I want to distribute this negative 4 radical 6 right here to negative 5 radical 3, let me write that down over here on the side now. Negative 4 root 6 times negative 5 root 3. That's the second step of distributing. What do I get when I multiply those two things, Paul? What do I get for the negative 4 times negative 5? Positive, right? And then root 6 times root 3? There we go. So now I take a look at this and I can see, all right, I can go further. I already broke this one into perfect squares. Now we got to take 12 and 18 and break them into perfect squares. What should I break 12 into? 12 is really what times what? 3 and 4. Now watch what I'm going to do. I'm going to take the root 4 and just write it as a 2 down here. And then I'm going to break up the 18. 18 should be broken into what? If I'm looking for, again, perfect squares. What perfect square goes into 18? Into 18.
9.
So we got 9 and 2. So I've got plus 20. Now root 9 is really a 3. And then root 2. So let me simplify all my coefficients first. 20 radical 3 minus 24 radical 3 plus 60 radical 2. How can I combine these? What terms can be combined? And think of them as variables. Remember, only like terms.
The 20 radical 2 and the negative 24 radical 3.
Yeah, the first two terms only. Okay, these two are like terms. So it's really 20x minus 24x, right? This is like 20x minus 24x and then plus 60y. That's what I'm thinking about. It's not really what's happening, but I'm thinking that way. So 20x minus 24x would be negative 4x. So negative 4 radical 3 gets carried down plus 60 radical 2. Okay, so again, I only combine these two terms that are underlined here because they have the same radicand when I'm adding or subtracting. This radical 2 is different. It's like adding a y, so it just carries on down. And there's nothing else I can do with this. I cannot simplify any further. Does that make sense what we're doing here? We're looking for like radicals every time. Part B is a little bit trickier, but it's not any more difficult, really. So let's take a look at part B now. Part B, we've got 4x times the square root of x cubed minus the square root of x to the 5th. Give me a first step for this one, someone. What's a good first step for this? When you don't have the same radicand, you can't combine like terms. So you should probably try and do what?
Break x to the 3rd down.
Okay, into?
X squared plus x.
Times x. And then the next one break into?
X to the 4th times x.
Good. Good. All right, so what Charles noticed right away is this. He said, you know what? These are not like terms, and they're not perfect squares, but x cubed is really x squared times x. X to the 5th is really x to the 4th times x. And these, the x squared and the x to the 4th, and the radicals are perfect squares. So we have 4x, absolute value x, radical x, minus, what's the square root of x to the 4th? Square root of x to the 4th. x squared. Now, remember this whole radical x thing? It looks like it's going to give us an annoying, well, it's going to be annoying here because it's going to throw us off and we can't combine. But think about it. It doesn't actually matter if x is positive or negative anymore because look out here. You have 4x times absolute value x. So outside of this radical right here where I'm pointing, it's x times absolute value x. That's got to be positive, right? You're thinking about x times x, it's going to be positive in the end there. So we're going to take this and just say 4x squared. Radical x minus. And then we can combine like terms. 4x squared minus x squared. Think of this as a coefficient and this as a coefficient. Okay, if this had been, ready, if this had been, let's say 4y minus 1y, it would just be 3y. This is 4x squared minus x squared, which is just 3x squared radical x. Remembering that whatever's out in front is like your coefficient. Even if whatever's out in front is a variable, it's still, remember, combine the coefficients and carry down whatever this is. And again, 4y minus 1y. That's what this is, 4y minus 1y. And finally, the last one. The last one. We're looking at a cube root here for this last one. It's a little bit longer of a process to do this now. So we've got for this last part 2 times the cube root of y to the 4th all over 3 plus 5 times the cube root of 2y to the 4th over thank you, 54. What approach in this case? Because this can be really messy if we don't take the right approach here. What should we do first? Give me a first step.
You make 2 cubed radical y to the 4th and simplify that to 2 cubed y squared.
Right here you're talking about?
Yeah.
Close. It won't be y squared, I can tell you that. It won't be y squared.
Y to the 3rd and then y.
Yeah, break it into y to the 3rd and y. So this first one, which you're on the right track to break up, I would break it into y to the 3rd. And then y, like that, okay? Because now I can have a cube root of a perfect cube. The whole goal again is to get these two things here. And when these reduce, it becomes a y. What about on the right-hand side? What should I do on the right-hand side?
Simplify?
Yeah, simplify. A lot of people forget that step. The 2 over 54, simplify that first. Because you're going to try and break up the 54 and then rationalize. That's a mess. Think of this as, right, this is a 1 over 27, really. Okay, 2 over 54 is really 1 over 27. And what do you know about the cube root of 27? See? This is 3. Cube root of 27 is simply 3. So I'm going to write this one up here. This one is really 5. Cube root of y to the 4th over 27. That's when I simplify the 2 over 54. And then the cube root of 27 is really 3. So this is 5 times the cube root of y to the 4th over 3. Again, the cube root is around the y to the 4th and the 27. So if it makes it more obvious, let me extend my radical a little bit further. Okay? So the radical, or the cube root of 27, this right here, this cube root part of 27 reduces to 3. And then the cube root of the numerator just remains what it is. But you'll notice that this numerator right here breaks up the same way this does. So let's break this down into y to the 3rd times y. And now we can clearly see that these are going to be like terms. Just look at the format. You see the exact same format for both of them. So if I want to go ahead and solve this, I'm going to simplify first to make this 2y cube root y over 3 plus 5y cube root y over 3. And a minute ago, Paul reminded us when we have the same denominator, what do we do to the numerators? Just add them together. So this is 2 as a coefficient. This is like a 5 as a coefficient. See what I underlined in blue? That's like a 2 and a 5 there. So the 2 plus 5 gives us 7. You've got to carry the y, and carry the cube root of y all over 3. So again, this is like your coefficient. 2y plus 5y is 7y. This is like your variable x. This is carried down. And then you have a common denominator, which means when you add the numerators, you just repeat the denominator. There's no change to it at all. Okay?